universal, hopefully, or many of them hopefully are universal. So we do have one paper on both arXiv and medRxiv. First time I've ever submitted anything to a medRxiv, but we have much more results, some fundamental basic changes that hopefully you see very soon. And we're going to talk about some of them. Don't hesitate to interrupt me. I don't know the format, but I'm happy to take questions at any time. So if you do go to our dashboard, and this is specific to the US because the data is much more comprehensive and homogeneous for the US, what you can do is you could enter any city or county that if you're interested in the US. Here I entered New York City. And then we basically run simulations on the cloud, starting at some time and starting some mitigation strategies. And the mitigation strategies could be social mobility restrictions, going from total lockdown to normal activity, could be face mask use, going from none to 99% face mask use, vaccination, and then you could run a simulation for 30 to 180 days. And the model is periodically updated so that there are a few parameters in the model, but the idea is, and as we're going to see, you have a handful of parameters, but then this is something that you use to fit thousands of epidemics in the US. There are 3,000 counties, over 3,000 counties in the US, and we fit 2,500 of them. And then here are the properties of the county that we find to be the most important properties that drive the epidemic. So, so the annual death in the county is important. There is the population weighted density that I'm going to talk about, population density, and a bunch of other properties that I'm going to talk about. And these are the things that we statistically identify as the most important drivers of the local epidemics. And here's an example of what you get for New York City. If you started, I actually cannot see this axis because of the Zoom thing. Okay, so that is September in New York City, and then ran the simulation, and the blue is what actually happened. And the orange region is basically a 68%, sorry, is a 9% confidence region for 100 simulations. So there are, of course, considerable uncertainties if you go to longer times, and that's the nature of the epidemics. And that's one of the things we're going to talk about. Canada world hopefully coming soon. The more help we can get, the better we can do this. But yeah, I mean, I think I'm going to hopefully try to convince you that this is an ongoing effort. It's not something that's going to be over soon, unfortunately. And it needs the attention that it deserves. Okay, so Roya gave an excellent introduction. In fact, I remember last time I visited Paris and I gave a colloquium, Roya introduced me, and my entire life flashed before me. So I was, and indeed it's, thank you to Roya for introduction. And indeed, this is not what I do for a living. So I do work on a variety of topics, what Big Bang looked like, how quanta gravitate. Can we see the dark universe? What lies at the bottom of the black holes? In fact, this is a picture of the echoes that Roya mentioned that we've been looking at. If it remains an interesting topic, active topic of investigation, and also very controversial, whether they're gravitational wave echoes or is there evidence for them. And these are all topics that many of you have worked on, are very interested in, but a topic that haunts most of us these days, more than any of these, is the pandemic. So why would an astrophysicist work on pandemics? I know some of you do. I know Gary has done that, and some others. And so some of you may already connect with this. Others may need more convincing. And of course, one reason is because we are all in this together. So we all have our own perspective, and we are all stuck in this, so we can all help if we can. The other reason is that we use complementary techniques and approaches, and this is a novel coronavirus. There hasn't been anything like this, at least in a century. And the last time this happened, we lived in a very different worlds with the 1918 influenza epidemic. So So even though epidemiologists are great in their work, this is the new challenge, and maybe we can use our complementary techniques and expertise to help. So this is something, in fact, I did for my thesis, and it's something that I'm going to try to stress. It's very similar to what we need to do with the pandemic. So what I did for my thesis, and in fact, is an active area in cosmology. We look at the Big Bang microwave light that came from the Big Bang. We look at the correlations with galaxy distributions. And from this, so this is, of course, many do this. This is in particular what I did for my thesis more than 15 years ago, 16 years ago now. We could unravel the other 99% of the universe. There are dark energy, dark matter, and in fact, most of the atoms, as you know, are also invisible in the intergalactic medium. And by studying this type of studies, this cross correlation of very different types of data sets, you could uncover these dark components of the universe. And the last thing I want to mention is that this beast, another reason that astrophysicists should work on pandemic is this beast has yet more heads, and we're not done yet. So I think we still need, there are still monsters there to be slayed, unfortunately. And we have some of the swords, some of the weapons that others may not. So here's a slightly more direct analogy. So the clusters of humans and galaxies, on the left, you see, I guess, a picture of I think, Columbia campus at New York City. And if you look at the distribution of people, you see that it's not random. The people are clustered. And in fact, I remember the first time I saw a picture of like this, Jim Peebles was giving a colloquium at the physics department at Princeton, and he showed a similar picture, saying that people are clustered. If you look at the distribution of people, you see they move around in groups, as do galaxies. So galaxies, if you take a picture of the universe, it's a CFA survey, Center for Astrophysics from in the 80s, and then many surveys that followed. They study these clusterings of galaxies. So you have clusters of humans, you have clusters of galaxies. And the analogy here is that if they are surrounded by the dark matter that we don't see, but we can infer based on the properties that we can see. So the right-hand side is a simulation of the dark matter that surrounds the visible galaxies in that simulation. And the left here, I kind of put in some pictures of the coronaviruses, which is what happened in New York City in March. And of course, again, it's happening last March, a year ago. And it's happening again now, everywhere across the board. So these are the dark matter that goes around the clusters of humans that we do not see, but it's something that drives their evolution. I mean, drives the pandemics. So to the questions that we want to answer is, of course, all of us are interested in this, but maybe we can help for answering it, is what factors drive epidemic growth and decay? Can we study diverse epidemics in demographics, settlement, weather, etc., to identify these factors? Then we need to appreciate that correlation is not causation. So we need a mechanistic or causal model to predict what's going to happen. There is an interesting question of whether herd immunity has been reached anywhere. And this is a question in which my answer has evolved over time. What are the best steps to manage and avoid future outbreaks in each community? And then what is the best vaccination strategy? So to put in very simple terms, in fact, the first thing that I started wondering about was, these are two different islands, Kodiak Island in Alaska and then Manhattan Island in New York. Do both of these places have to go into lockdown when the pandemic hits? That's one way of asking the questions that I was asking in much more detail, that do we have community-specific recommendations for our policies? So we have a novel predictive framework that we've been kind of working on over time, and it's been improved over time. So on the left-hand side, we have things that are traced nowadays via various proxies. And this is the novel thing that we're using. We're bringing into epidemiology thanks to novel technologies. We have social mobilities that are tracked by cell phones. We have traces of face mask use and social distancing, either via surveys or via internet searches. We have weather, of course, on a local level. We have population density and sparsity that's now mapped to high precision or to high resolution across the globe. We have demographics, and then we have immunity based on vaccination or prior infections, right? So these are all the data. These are basically like your galaxies, if you want, things that we can see. And there is, of course, there is the COVID itself, the mortality and cases that we see as well. So these are all the visible things. What's happening behind the scene is a epidemic. You have incubation and transmissions. That's basically, so you have transmissions that are traced, and then you have incubation that you don't see, but you see its outcome that leads to either death or to cases. And we have different models for this. And our strategy is basically to assume that consider whether a universal model with, say, 12 parameters could fit 2,500 distinct epidemics over 400 days. So we have over 100,000 data points for growth rate of epidemic at various communities at various times. You want Cheetos? Oh, sorry, I'm in the middle of a meeting. Sorry, I cannot. You can get the scissors themselves. Okay. Okay, sorry. I think maybe I can. Sorry, I'm in the middle of a meeting. I cannot do that. Okay, sorry about that. Okay, so that's kind of the idea, is that most of what is done in epidemiology are the toy models that they cannot make a specific forecast. They just tell you basically what may happen if you do this in this toy model. And the forecasts are really just extrapolations based on the past in most of the models. They are not a single universal model that could be applied to everywhere. They fit the parameters for specific communities. And the idea is we think they are universal parameters. Okay, so so let me see in the next 20 minutes. So this is kind of the outline. I'm going to try to go through this quickly. So what is the data that we're using? So we have some static data sets. There's a demographic data from US Census. We have population weighted population density. So this is something I'm going to talk about, but this is in fact the main working horse for our model. Our approach is that we're tracking a clustering of humans around each other. I'm going to talk about this in a minute. Because we use population sparsity, which is another measure of clustering of humans. And these are directly analogous to what we do with galaxies, in fact. And then we have some time series data. There is COVID-19 data mortality in case that's now tracked by Johns Hopkins University and New York Times. There is weather data. There is human mobility that's tracked by Google. It's also tracked by Apple, but we use Google data. There's Google Trends data and face mask that we use just as a proxy that's as comprehensive as possible. And most recently, there's vaccination history that we use our analysis. So these are the kind of data set that we use. And the idea is that basically try to fit an epidemic model, a global, or at least across the US, a universal epidemic model to all these data. So the working horse I was telling you about is population weighted density or lived density. So basically the definition is that you average the density. So you average the density of people in 250 square meter parcels weighted by the population in each parcel. So if you imagine these are two counties, one is, they have the same number of people in them, but one is bigger than the other. So clearly the density of the people on the right is less than the density of people on the left. However, these people live in dense parcels, neighborhood cities, you can imagine, and there are all these empty places in between. So the population weighted density is the population density, but weighted by the number of people in the parcel. So the parcels where nobody lives, they have zero weight. So that means that these two counties have the same population weighted population density. So in other words, everybody, if they look around them, they see the same density of people within 250 meters. Even though if you go farther away, they may not be the same, but within a close proximity, they see the same density. So that's the idea of population weighted density. And you could see this is already very closely related to correlation function. In fact, Jim Peebles, who many of you, most of you, I imagine, know, and he won the Nobel Prize in 2019 for his pioneering work in cosmology. He pioneered this study of correlation functions. And here I'm showing one of the early works on projected correlation function of galaxies, where you look at basically density of galaxies in the sky as a function of separation. So basically, how likely it is to find another galaxy in proximity of one galaxy. So this is a galaxy correlation function, and then you could do human correlation function. Human correlation function would be essentially the same thing, how the density falls as a function of the parcel area in this case. And the same way that Peebles and Davis fitted a power law to this, we could fit a power law to this, to the rate of fall off of population weighted density with distance or area in this case. And there's a power, which we call it population sparsity. For example, for a uniform distribution, it's, this power is 0. But for a sparse distribution, the example I have here is 1/3. So the number can go between 0 and 1, depending on if you just have one pocket of population, it would be 1. That's the most sparse possibility. And the most uniform possibility would be gamma of 0. So, so these are important because, of course, the epidemic comes from transmitting viruses in proximity. So the more people are in your proximity, then the more efficiently you can transmit the virus. But of course, the more sparse the population is, the harder it would be for the virus to be transmitted over larger distances. So here the virus could go either way in every direction. Here the virus could be transmitted in one direction and then the other. So based on this, you can see both sparsity and population weighted density are important for determining the trajectory and efficiency of transmission. And I should say, nobody has actually studied this in epidemiology, and we kind of directly imported this from cosmology. Other data sets that we use, this is average mobility tracked by Google. You see there is around 0%, it's a baseline, and then around the lockdown times, they all dropped to, in New York City, minus 75%, LA minus 50%. And these have been tracked to this day. They have been rising and falling depending on local conditions. Here, the case incidences that early on was exponential in various places, but then either for various reasons, they stopped or started going down. We're going to discuss why that happens. But basically, our goal is to understand this dynamics of cases and mortality based on local conditions like the average mobility and temperature and other things that we looked at. So this lambda is exponential growth right here. Any questions so far? Okay, so what we did is first try the linear model. And in fact, we first tried, this is something that Ben did. He tried to fit the early growth rates, these exponential growth rates, to basically to linear correlations or linear regression with various drivers like average mobility, the population density, and so on. And we had significant correlations. There were very significant, like 11 sigma correlation with mobility. There is 5 sigma correlation. These are only for early epidemic in March and April last year. 5 sigma with population weighted density. The correlation with sparsity. So the more sparse, the slower the epidemic is. So that's why it's a negative correlation. Humidity, and in terms of temperature is the same, has also a negative correlation. And there is dependence on median age. So these are very early data. All these significances are now much, much higher as we look at later data. So just something to keep in mind, but this is the first thing that we did, but all of these are much, much better determined now. So what we did next was to extend this early time analysis to all the times. And what we do is we look at this exponential growth rate or decay rate. So it's basically logarithmic derivative of daily mortality. And we do it over a 14-day period to basically fit a line to it. And for this, we use mortality statistics because it traces incidence of growth, incidence growth rate with some delay, but it's not dependent on testing rates, which was a big problem early on. Testing was not done regularly. And even nowadays, testing policies do change from time to time. So mortality is a little bit more reliable, although it is affected by other things. And as of now, we have 10 to the 5 growth rate measurements across time and counties. That's 400 days, 2,500 counties. We can use a linear regression to find significant drivers, and then we use a nonlinear epidemic model to fit for to find a more precise model, because of course the epidemic is not a linear process. You have outbreaks where you have fast growth, but then you end up, you reach a peak, and then you have exponential decay. And these are not linear models. So basically, you have a positive growth where it's very nonlinear, and then you have the exponential decay that doesn't depend much on local properties, it turns out. So that's the idea. And then, so I'm not going to take you through the nonlinear models in terms of that there are different ways of doing this, but these are basic epidemic models. You have exposed, infectious, hospitalized, and death. And the idea is you could have basically people being exposed, then becoming infectious, and then the people who are infectious can expose other people. And this is the way the epidemics works. So we had a random walk model for this, but you could work with other models as well. And the idea here is just a simple cartoon. These are the different people. The red is infectious. Susceptible is green. So there's healthy people who have been who are not sick yet, and they're exposed who are people who are exposed but are not infectious yet. And what you see is happening is the people move around, and there was this green person who becomes blue. Can try this again. So this, you see, look at this green guy down here who is susceptible. He crosses paths with the red guy, and then it becomes blue, so he's exposed. And at some later time, this person could become infectious or may not become infectious. So not all the people who are exposed become infectious. It turns out only a small fraction do. So this is basically like a molecular collision or atomic collision process. And you could compute, there would be a cross section, there's a relative velocity. This is basically what we can do in chemistry or in plasma physics, if you wish. The only thing that's different is that there is a delay that, so first of all, yeah, so there is, the person who's infected is not going to be infectious right away. There will be some time before they become infectious. So that delay is something that should be taken into account. So I'm not going to write down the result of the model, but this does lead to exponential growth with some parameters. So we find this model that fits all the data. The reduced chi-squared is somewhere between 1 or 2, depending on exactly how we do this. So on the right, I have some of the examples of what we get for the epidemic growth. This is Chicago, or Phoenix, Arizona, Los Angeles, this is Miami, where else is New York City, and then Detroit, Michigan. So the red is the best fit model, is the model that comes from this universal parameters. So as I said, there are 2,500 counties, 10 to the 5 data points, but there are only 10 parameters or so, over the 10 parameters. So, and this is how well it fits. And the reason it fits is that basically there are local drivers in each community that you use to get the red curve. And the blue is what actually happened in terms of the mortality growth rate. So there are some parameters that we measure. There are some that are intrinsic to the disease, more or less. There is basically the incubation time, roughly, which looks like a large number, but it's not really this large. It says 100 days, but it's not actually incubation time. There's some recovery time, which is around 20 days. There is some rate of immunity, and then there are some properties of the transmission. There's some normalization and how the transmission depends on human mobility, on a specific humidity or temperature, on population sparsity, and on there's some dependence on annual deaths, which if you're interested, we can talk more about. So let me try to, okay, I'm just gonna go faster. So let me just give you some highlights of what happened. So that's what we had back in July. So this is the model as it stands now. It has a few more parameters because some of the things we identified better. For example, before we didn't have dependence on household because it wasn't very significant. But now the number of people per household is important. It seems that that's a significant driver. With more data, it just became clearer. The dependence on humidity or temperature, we usually have a linear dependence, but it looks like it's not a monotonic relationship. It could change sign. So we have added all this stuff now, and this is the model as it stands. So there are different ways of seeing how it does. So here is basically the residuals, the measured growth minus the model growth divided by the error. As I said, there are 10 to the 5 data points that go in here and 10 parameters or so. And you see that there is basically the residuals are roughly what you expect them. So this is a 68% confidence region for residuals, which is between -1 to 1, which is what you expect basically. Sometimes it goes up and down, but on average, it seems consistent with what you expect. This is the logarithmic growth rate averaged across the US. You could compare it with the weekly COVID death that's reported. So essentially, these are the logarithmic derivative of these guys, the reported death. And you see basically there are 3 major peaks here, right? The first, second, and third peak. And then the growth rate was really the biggest at the beginning of the peak, right? As you're rising up. So this is the early epidemic where you had the biggest logarithmic growth rate here or here. And then this is the second peak. You had this peak here where it goes up. And then the third wave, which was the biggest one in the early winter, late fall, which is this peak here. And blue is what the model tells you, and the red is what actually happened, right? And blue has also a band, which is uncertainty, basically. So that's kind of, so the model seems to be doing okay. And you may ask, if I use a model that was fitted, say, to early data, how well it does in terms of predicting the late time data. And this is kind of one attempt to show that if I use all the data to find the best fit model, then I would get this. But then if you just use the model pre-September and try to predict or forecast what happens into the future, given the drivers, given the social mobility and weather and the epidemic history, everything else, then you get something that's not very far off, but it's not exactly the same thing. So the model does change, the best fit parameters do change. So you see that if you use just September data, you wouldn't have gotten as big of a peak as you did actually. So there are some things that are happening that are not completely predictable. It could be the variance, which is, I think, a topic I'm going to keep going back to, or it just could be that the disease is evolving or humans are evolving or something like that. So our reaction is not really what it used to be. But the point is that we are using all the possible predictors that we can trace. And this, in spite of that, of course, there are things that we cannot predict. So these are some examples of county by county predictions and compared to how well they did. These are 4 corners of the US. And yeah, some of them did better than others. This is an earlier version of the model, I should say. This is an example of what the face mask would do. Again, this is based on early models, earlier models. Our model is a little bit more sophisticated now, but this is what we would have predicted back in October for what if you had 100% use of face mask or no use of face masks, and what difference it made. So face masks did make a difference based on all the data that we had, but of course it's not the only thing, and it's not the most important thing, as it turns out. So one question that is very controversial is the question of whether we reach herd immunity at some point. And I'm not going to, basically the question of herd immunity is whether the epidemic is growing or decaying after you remove all the social restrictions. And sorry, let me, before I get there, I think I skipped this plot. So here's the dependence on face mask use. This is how the growth rate of epidemic depends on face mask use. So if the more people use face masks, the slower the epidemic gets, but on its own, it's not enough to stop the epidemic. This is the dependence on temperature that, as I told you, it's not monotonic. In fact, it's somewhere between 20 to 25 degrees centigrade. It seems that the ideal temperature. And at much higher and much lower temperatures, it makes sense that people don't go indoors, and that's probably the reason the pandemic or the transmission is more efficient. So 25 degrees, 20 to 25 degrees seems to be the optimal temperature to minimize the epidemic. Maybe not so coincidentally, that's also the mean temperature of New Zealand. So maybe that's one of the reasons they're doing so well. Okay, so I'm running out of time. So basically, about the herd immunity, we had early evidence that if you use all the models that we're using, assuming that there is permanent immunity, then some places do reach immunity, and these are kind of this is daily mortality versus total mortality. And we found these trajectories in our model, and there's a fixed point, which is the herd immunity threshold. So the idea was that if the countries or counties pass this point, then they become, even if they release all the social restrictions, the epidemic won't be growing. So it's like a phase diagram for the epidemic. And the social mobility restrictions could bring everything down, but even without social mobility restriction, there is a fixed point somewhere. And then we kind of found this for various counties. For some of them, it is lower. For some other counties, it was higher. Unfortunately, one thing that later became clear was that the immunity that we were fitting for is something that may be important in short time, but for longer time, more than 2 months, it becomes less important. It's not that it completely goes away. It's just much, much less important than it was in the 2 months. Now, whether this is a biological thing or a sociological thing, it's hard to tell from our analysis. But basically, it seems that there's something that's within 2 months could slow down the epidemic after infections. But beyond that, you lose the memory, either social memory or biological memory. So this comes from global analysis of all the data, that basically beyond 2 months, there is much less immunity than there is within 2 months. Could it be due to the variants? This is one example of one thing that came out of our model. If you look at the LA, you had this huge outbreak that couldn't be explained. Our model didn't see anything like that, but there was this huge peak, basically many sigma above the prediction of the growth rate. And this is around the same time that these variants in various places started coming out. This is an article from LA Times regarding the variants in LA or in California. So that's, maybe that's responsible for the loss of immunity. It's hard to tell, but it's kind of fits the bill. So let me conclude. So this is where we are. Unfortunately, I don't have a clear message for you. We do have a pan-epidemic approach to epidemiology. I think maybe the clear message is that we could, if you use a physical astrophysical approach, we can understand things better and connect them. And we think it is more predictive and physical and useful than traditional methods in epidemiology. We can tell you about the community-specific interventions because we can quantify how things depend on population distribution, demographics, climate, by studying the diverse set of epidemics. But there are open questions. So what are the best ways to track social distancing or population or PPE or face mask use? We don't know. And optimal vaccination strategy, that's something that can come out of our analysis because we can tell you where the epidemic grows faster and who it affects most. And then those would be the places or the people you want to target. So basically the idea is that you want to focus on places where you have denser populations. That's the shortest message you can get out of this. And I think the biggest question for me is that how do you balance the harms of these various mitigations against other adverse effects like on mental health, economies, education, parents, children, etc. And that's a much harder question and much longer term question. But the tools that we have can help in that direction. So at the end, you may think this is over, but unfortunately it's not. And this beast has yet more heads, such as these variants that you keep hearing about. And I think we need all hands on deck to understand what to do with these, because I don't think the vaccines will be a panacea. Vaccines will be one of the tools that we can use, but they will not end this. And we still need to understand this better and know where we can use the artillery of weapons that we have. Okay, thank you very much.
Thank you, Niayesh. Any questions for Niayesh?
Okay, can I ask a question?
Sure, Gary, go ahead.
So what you did is absolutely amazing, all right?
Thanks, Gary.
Very, very complex modeling. I like it a lot. I didn't understand a few things. For example, since there's the death rate goes exponentially with age and is also affected by other factors like obesity, which you could track. So some people, they use matrices of social interactions between age groups.
Yes.
And I was wondering if you do that too.
Right. And no, we don't do that. So, I mean, in principle, you could make this arbitrarily more complicated. But the question is, we wanted to use as little as possible because the thing that if you have a lot of free parameters, but you don't know what they are, then it's not a very useful model. So we basically introduce it's like we use Occam's razor. Since that we're not doing a fundamental model of everything that's happening, we're doing an effective model in some like fluid mechanics. So we have like effective parameters that describe interaction of people, but then we don't describe the microscopics of how that happens. And it's like measuring viscosity and I don't know, temperature and things like that. So that's kind of our approach.
Still in your fluid approach, so you consider median age, right? And you consider death rates, which might be a proxy for obesity and other health factors, if I understand. Even though you could probably also get statistics on obesity independently, I'm not sure.
Yeah. I mean, we have some of that. In fact, I had median age, but now we are using the age distribution. So that's an extra factor. So in fact, the most important thing we find that is the fraction of the population above 80 years old. That's much more important than median age. But then there could be other health factors, indeed. I mean, I think we tried adding a bunch of things. Some of them, you see, the problem is that some of these are all correlated with each other. but yeah, like the health issues, that we haven't included that. But yeah, certainly that's another thing that that could be helpful to include in terms of if they have healthier population or less healthier population. Yeah, I mean, I think that's an excellent idea to include that as well.
I'll stop there to let other people ask questions, and maybe I'll ask more later.
Yeah, thanks.
There's one by Florence. Go ahead, Florence.
Hi, I was just wondering, a few slides before this one, you showed the variation with temperature, and
Yeah.
I sort of understand that if it gets colder, people stay inside and there's more contamination. But
Yeah.
why is it the same when it gets hot?
Yeah.
Is it just valid for countries where you have air conditioning and people stay inside?
I imagine that might be. So this is limited to the US. So I think France might be very different.
Yeah.
Yeah. But this is kind of very clear that we get, and this is also, yeah, in US, when temperature goes above 20 something, then everybody goes inside and air conditioning. Yep, that's right. It's very American, possibly.
Yeah, I think so. Thank you.
Thanks.
There's one on the chat by Alexandre, and actually I wanted to ask kind of the same one. Sure. He says, I have a very stupid question, but as an astrophysicist, I am not sure I can say whether your model is convincing. Are there any epidemiologists involved in your work? And I was going to ask the same kind of a parallel question. I mean, how is this model doing compared to more traditional epidemiologic models?
Yes, so that's an excellent question. And so I think we have certainly some elements in common, which is we're using some model of infection, this SEIR models. We use some version of that. The part that's different is, so in traditional epidemiology, you just fit this for every community, but for every community has its own model and parameters. For what we do, we actually identify what sets those parameters for different communities. So we did this, I think, so the background of us is physics and astrophysics. My collaborator, he worked on modeling viruses in humans, so virology, not epidemiology. We have reached out to a lot of epidemiologists. They're all very busy, I'm sure for very good reason. So they just don't respond to our emails. I've given talks for them. Yeah, but I think at some level it's understandable because, I mean, they're all very busy with their own modeling. But it's hasn't been for the lack of trying. So we just got silence for the most part, basically.
Okay, so you haven't got some feedback from epidemiologists yet. Okay. Yeah,
no, we have not.
Workshops of epidemiology.
Well, I mean, workshops of epidemiology I mean, I think everything is happening online now. So I've given talks to them, but I haven't really seen a workshop per se. So I don't really know. Yeah, that didn't happen to us. Yeah, so
I've attended one that lasted 3 days, and I was able to make some, and it was very interesting.
That's great. Did you give a talk there?
I didn't give a talk, but I expressed my. I made a resume of my paper in 1 minute.
Yeah,
it was interesting.
Yeah, I mean, yes. So our paper is published in a proceedings, because that's where we submitted it. Our second paper, we hope to submit it for kind of a more serious journal. But so this was for there's a mathematical modeling basically seminar series at Fields Institute that our paper was submitted to. Yeah, so I think in terms of, it's kind of funny. We submitted it to a couple of journals, and they just said, this is too fine, too detailed, and we only publish more general things. And then we just didn't try much more than that, because I think it just, it took too long.
I have a problem, all right? So I submitted, I looked for a journal which accepted LaTeX and which was free.
Yeah.
So an epidemiologist said, try mathematical biosciences.
Yeah.
So I studied mathematical biosciences, and the day later, the editor wrote to me and said, your paper is probably not wrong, but it doesn't bring anything to the science of epidemiology. And I wrote back saying, that's not my intent. My intent is to make the country, France, understand what the situation is. It was at the time of just after the lockdown that I published this submitted this in the mid-May. And so it was after the lockdown to see whether, what was the arc factor before the lockdown and during the lockdown. And I got it right for those things. And I also made some scenarios.
Yeah.
And this is information that is important for the community to know. And if you don't want to publish it, that's fine. But could you at least give me the name of a journal that might be interested? And he never replied, and I went back to astrophysics.
Yeah, yeah. That's a bit unfortunate. I think at some level, the barriers is understandable. If you imagine you work on black holes and then an epidemiologist writes a paper on black holes and send it to you. I mean, yeah, so we do get some of those. So especially during this time that's very political, I understand this, and I think we try our outreach to be as best as possible, but yeah, we also have the other things we have to focus on. So I'm still working on reaching out to epidemiologists. If there is anyone in the audience, I don't think so. I respect their work very much and hope we can contribute.
One thing I noticed is that the papers by the epidemiologists kind of simple. All right, they don't show all the details. In other words, if they were doing astrophysics, the referee would give them a hard time. And especially the papers on medRxiv, which are just for journalists. Okay, so they just give minimum information, you know, and it's you know, I found it a little bit disconcerting.
Well, I think it's important to be understanding of, I mean, that there are different cultures and they have their own, yeah, I mean, we can all criticize each other in various ways, but yeah, it's, I think we should try our best to do outreach. I admit that maybe I could have done more, but it's hard to reach out to them, unfortunately. So I mean, we did a little bit as you did, but these are not ordinary times, unfortunately. Yeah.
Are there any more questions for Niayesh before we conclude?
I have more.
Okay.
But if others want to, so I have just one comment and two comments. One is in France and probably elsewhere, people are measuring the circulation of the virus in the sewage.
Right.
Very effective. That's one thing.
That's great, yeah.
The second thing is that there's now data on the variants. All right. So in France now, it's maybe not systematic, but now they test for variants. Once you're tested positive, they try to find out what variant you have. That's very useful. And the third comment I have is that, to me, a big factor which you did not take into account is the isolation of a country. Okay, so island countries like New Zealand, even Australia, South Korea, which is effectively an island because of its unfriendly border, they did very well. Okay, Taiwan. Then I used to say Israel used to do well because it was effectively an island, but then they had a very bad second wave. Okay, so that disproves my idea. And then in Europe, we refused to close the borders between countries, and that cost us tremendously. Okay, it might have been good economically, but you know, I think we could keep the borders open for truck drivers and close it for tourism, right? And even for family reunions, we should have closed the borders, but we refused to do so. And that cost us a lot, okay? And within countries, especially large countries like the United States, the same issue comes, you know, should you prevent travel between borders, between the regions, between states in the United States, or whatever?
No, I think that's an excellent question. That's something that's a bit harder to quantify from our approach because ours is very local. But I mean, I really want to think that there are two different questions. When does an epidemic start? And then the other is how fast it grows. And the growth of epidemic is a community transmission thing that happens locally. But then the onset is when you introduce a virus into a community. And that happens through the borders. And like, for example, for New Zealand and South Korea, well, I mean, New Zealand and Australia, I would say South Korea, I'm not 100% sure. Basically, their epidemic never started because the virus was never introduced, so that whenever it was introduced, it was suppressed very quickly. So that's one thing. But then if it is introduced, how fast it grows, it's a mitigation strategy as opposed to suppression strategy. And so what we can quantify is the mitigation strategy, that if the virus is already there, what determines how fast it grows. But then, of course, the best thing is not to have a virus at all. And for that, you want to close the borders and do all sorts of self-quarantine. So that would be a suppression strategy, which would be more related to the what happens at the border.
Because in cosmology, the equivalent of this cross-border circulation is the baryonic oscillation peak. Okay, the BAO peak gives you this extra correlation, you know, in large scales, even though it's very, very small, you know.
That's similar. Anyways, I think it would be cool to do more cosmology with pandemic. So if anybody is more interested, don't hesitate to write to me. And thanks a lot, Gary, for the questions. Maybe,
And I have one more comment. Because, in France and other European countries, we're playing with curfews. So partial lockdowns, they're lockdowns in time and not lockdowns in space. So this is an interesting thing to try to quantify.
Yeah, if we could get data on that in the sense of actual, say, daily cell phone activities or things like that, so the nice thing about cell phone activity is that it tells you what actually happened as opposed to what the rules say, because the rules are not very good if the people don't listen to them or don't obey them. So then the question is, but the cell phone activities that track what actually people do. And then so that's the kind of data that we use, but it's somewhat limited. So the curfew, I'm not exactly sure how to track that, but that's a great idea.
And why did you say that face mask? Okay, so they have a reduction, which you show in your plot, but this is not the main factor. Because if everybody wore a face mask and if everybody forced themselves not to eat together, then we would get rid of the pandemic.
Well, I mean, again, there is a question of between the reality of what happens and the ideal situation. And the reality is that we have people have a range of face mask use, and not everybody would do it perfectly. And we just look at the range that has happened in the US and said within that range, this is what they do. In some ideal situation, maybe they would do much better. Okay.
Okay, thanks a lot. I think we should conclude. And thanks a lot, Niayesh, for this tremendous amount of work. Oh,
that wasn't me. Okay.
Okay.
Okay. Thank you very much. It's great to see you guys. Let me just stop sharing here. Okay. Good.
That was great, Niayesh. Congratulations.
Thanks a lot, Gary. Hopefully we can help more everybody. And thanks a lot, Roya. It's good to see you again.
Bye. Bye, Niayesh. Bye, everyone.